right, so in this chapter, we're going to talk about the chemical basis of life. Remember how living things were organized and they were made out of smaller pieces, and those were the chemicals. And then the chemicals formed the organelles, which formed cells, and then cells could work together to form tissues, etc. So we need to start by talking about the chemical level of organization in order for you to later understand how cells work and how living things function. So this picture is sort of an overview. We're going to come back to this later, but the question, if you look at this picture, it's a beautiful coral reef. The question is, how might a chemical compound in the air harm coral reefs? And we're going to come back to this at the very end of the chapter, but a little preview. So if we increase our carbon emissions, the amount of carbon dioxide in the atmosphere, things like auto emissions and factory waste and things like that, that carbon dioxide can dissolve in the water, and it can make that water acidic. It can become an acid, and then we're going to talk later about how that might damage coral reefs. So life's chemistry is tied to water. One of the things we're going to talk about in this chapter that will be very important are properties of water and why water is so important for living things. So for one thing, the first life would have been microorganisms in water. Second, all living things, of course, need water, and our cells actually consist of almost 70% water. So water is going to be a very important concept at the end of this chapter. So here's sort of an overview. We're going to start today by talking about elements, atoms, and compounds. We're going to talk next time about chemical bonds, and then we're going to wrap it all up by talking about the characteristics of water and why water is so important. So let's jump right into atoms and compounds. So first of all, living things were made out of matter. Remember, matter is anything that takes up space and has mass. There's about 25, so on the periodic table there's something like 112, 115 elements. We are made out of just 25 of those. So all those elements on the periodic table, about 25 compose living things. And only four out of all those elements on the periodic table make up about 96% of our weight. So, and those four, skipping down here, carbon, hydrogen, oxygen, and nitrogen. So one way to remember this is to think CHON. Carbon, hydrogen, oxygen, nitrogen. Those are the four most important elements that compose our cells. All right, so element versus compound. So an element is the simplest form of matter, made of atoms. A compound is a substance that's made of two or more different elements. For example, H2O, water, or CO2, carbon dioxide. These would be compounds, whereas carbon by itself would just be an element. And, trick question, O2 would also just be an element. Even though you have a 2 here, even though it's technically made of two oxygen atoms connected to each other, O2, it would still actually not be considered a compound because they're not two different elements. It's two of the same element. So just keep that in mind. Showing you here, interesting, sodium is an element. It's actually a metal. It's a very reactive metal. When you think of sodium, you usually think of salt. But sodium by itself, the element, is actually a shiny silvery metal that actually will burst into flames if you drop that in water. Chlorine, the element, is actually a gas. It's actually a toxic, green, strong-smelling gas. But when those two combine, we get a compound, sodium chloride, which is table salt, which you put on your French fries. And table salt has different properties, has different emergent properties that don't exist below the level of the table salt. So the characteristics of sodium and chlorine are not seen when they combine into sodium chloride. So a compound will get totally new properties compared to the elements that it's made out of. And so that would be an emergent property. The sodium chloride is a solid, whereas chlorine by itself you can see is a gas. It's also not toxic, whereas the sodium and the chlorine would be. And so the properties change in a compound compared to the elements. Here's the picture I was talking about remembering CHON. So see how much of our body is made out of just these first four. Carbon, hydrogen, nitrogen, and where's oxygen? Oh, there it is, oxygen up here. So there you go. Carbon, hydrogen, oxygen, nitrogen, CHON. Those four things make up a majority of all of our cells. Now there are other things, calcium, potassium, sulfur, and then there's some things we need only tiny amounts of. See this at the bottom? These are called trace elements. So let me show you these. So here's a little bit about trace elements. So trace elements are things that we require just in tiny, tiny amounts. And a couple of examples are given in your book, so I put a couple of them here. Fluorine or fluoride is actually necessary. It helps prevent cavities. And so we actually have it added to our water supplies. And that way, in our country, it helps to prevent cavities. It's also put in toothpaste. You've heard of fluoride toothpaste. So that's a micro element or a trace element that's needed in just small quantities. Other chemicals are added to foods for various reasons. They might help preserve it. They might make it more nutritious, or they might just make it look better. But sometimes different chemicals are added, and sometimes it's not necessarily a bad thing. We think of chemicals being bad, but for example, iron is added. Most cereals and flour and grain products are what are called fortified. They've actually added iron to them, and that's actually to solve a problem because iron is necessary for our red blood cells. You can become anemic if you don't get enough iron in your diet. And so by adding iron to grain products, everybody gets enough iron in our country. Iodine is another one. Iodine is, again, a micro element or a trace element needed in tiny quantities, but it is necessary for your thyroid gland to function properly. And we have iodized salt in this country. So table salt, when you buy salt in the store, you'll see that you can buy iodized salt, and it contains iodine. So it's a necessary ingredient, and these are things that have been added to our foods to make them more nutritious, just to give us trace elements that we might otherwise be lacking. Okay, so let's talk about atoms. So atoms, each element is made of just one kind of atom, right? So oxygen is an element consisting of oxygen atoms. Carbon is made of carbon atoms. Gold, Au is gold. It's made of gold atoms. It's the smallest unit of matter that still has specific properties. For example, carbon has completely different properties than oxygen. But if I just took a proton out of carbon or oxygen, they would be identical. Protons are all protons. They're all the same. Electrons are all the same. Neutrons are all the same. So I couldn't show you a neutron and say, hey, what element is this? It's no element. It's just a neutron. But the smallest thing that would maintain specific properties of matter would be an element. So the subatomic particles, protons, neutrons, and electrons, let's talk about those very quickly. So the neutrons and the protons are in the nucleus of the atom, in the center. So this is the nucleus. And then you probably remember hearing about the electrons. They're sort of going around it in a cloud, this kind of space. And you'll learn a lot more about this in chemistry. But for our class, that's just some general stuff you should know. Now, neutrons are neutral in charge. That's actually where neutron comes from. Protons are positive in charge, and electrons are negative in charge. And that's actually really important because we're going to talk in a little while about how protons and electrons are equal to each other in an atom, and that's why atoms are neutral normally. They don't normally have a charge or an electric charge in nature. Now, what gives the atom its identity, I mentioned, is the protons. So, for example, if it has 6 protons, it's always going to be carbon. If it has 8 protons, it's always going to be oxygen. If you change the number of protons, you change it into a different element. So that's very important. And that's called the atomic number, the number of protons that a particular atom has. Okay, so each element has a unique number of protons. That's its atomic number. Now on this periodic table, that's these numbers up here. And you can see it marked on this carbon one at the top. So see number 6, number 7, number 33, number 82, number 79. There's gold right there, number 79. So that's the atomic number, and that's the number of protons. In fact, that's how the periodic table is organized. It's in order of atomic number. All right, the mass number is the protons and the neutrons added together. So, and normally this is written, sometimes when you see this, there's a notation called AZ notation. So you might see this, 816 for this oxygen. So the 8 down here, this is the number of protons, this is the atomic number, and this is the mass number. The number of protons plus the neutrons added together. Now the atomic mass is actually an average. It's a decimal. In fact, I'm going to go back a slide really quick. So see these decimal numbers here. These are called the atomic masses. So notice how they are decimals. So for vanadium, V here, it's 50.94. This is basically the average of all the different isotopes that exist of this atom in nature. We're going to talk about what an isotope is shortly, but it's not the same thing as the mass number. So a particular atom would have a particular number of protons and neutrons, and it would have a mass number. These numbers on the periodic table are averages. Sort of like if I say, hey, how many kids are there in every class at McCarthy? And you say, oh, well, the average is about 30.5 kids in a class. That would be sort of like the atomic mass. You're not actually going to go into somebody's classroom and find 30.5 kids. You might find 32 in one classroom and 28 in another, and the average of all of that is going to be a decimal, but in an individual room, there's going to be a whole number. And that's the difference between atomic mass and mass number. So we'll talk about this a little more, but so isotopes of an element are basically where there's the same number of protons, but they have a different number of neutrons, which means they have a different mass number. So for this checkpoint question, it says that a nitrogen has 7 protons, and its most common isotope has 7 neutrons. The radioactive isotope has 9 neutrons. What's the atomic number and the mass number of the radioactive nitrogen? Well, let's start with atomic number. So nitrogen, they just said, has 7 protons. That's never, ever, ever, ever going to change, even in an isotope. So the atomic number is going to be 7 in both nitrogens. Now, what about the mass number? Well, the original nitrogen had 7 protons and 7 neutrons. So its mass number, which actually is usually written up here, is 14. But the isotope had 9 neutrons. So it still has 7 protons. It has to because it's nitrogen. And then 7 plus 9 gives me 16. So the mass number of the other isotope of nitrogen would be 16. Now this is just a different format, a way of writing it. You write the mass number up here and the atomic number down here. But the important thing to get from this is that if you know the protons and the neutrons, you can get the mass number. And if you know the mass number, you can figure out, and you know the protons or the neutrons, you can get the one that's missing. So let me show you. So here's carbon 12, carbon 13, carbon 14. So all carbons, see this? They all have 6 protons. So this would be 6, 6, 6. Now carbon 12 has 6 neutrons, so its mass number is 12. Carbon 13 has a mass number of 13, 7 neutrons. And then carbon 14 has a mass number of 14, and it has 8 neutrons. So notice how in the different isotopes, the number of neutrons can change, but the number of protons doesn't. Notice they also said that they all have 6 electrons. That's because atoms in nature don't usually have a charge, so the number of protons and electrons should be equal to each other. That way, this is positive and the electrons are negative, and they would cancel, and so it would be neutral. So this is a little table to fill out. So if we know the number of protons, and this is silicon 28, that's telling me its mass number is 28. So then if we want to get the number of neutrons, since the protons plus the neutrons give us the mass number, 28 minus 14 means it would have 14 neutrons. And then our electrons and protons should always equal each other, unless it has a charge, and they don't mention this having a charge. So this would also be 14.